Hey, what's going on, guys? Let's do this problem right here. So the first question is asking here that is define static dynamic and hydrostatic pressure. Let's see how we can define this. Okay, let's put this one. Put this first question as 1. So first of all, what is static pressure? So static pressure, actually that's the actual pressure of the fluid. So we tell that one as P. And the second question is, what is dynamic pressure? So if you don't know what is dynamic pressure, we give this one as rho v square by 2, and that is actually when the fluid in motion, and suddenly when it in motion, and if we bring that one into stop, what is the pressure change during that time, right? So that is what we call dynamic pressure. And then this is all in one. And then the third one is, what is a hydrostatic pressure? We give it as rho gc. It's like potential energy, right? It depends on the height. So if this is not actually a pressure, it depends on the reference, like the height from the reference level. So that is but it has effect on weight and pressure, right? It has effect on weight and pressure. That's all we can tell about this hydrostatic pressure. So this is how we define these three pressures right here. Let's do the second problem. So they have given a 10 centimeter, the tank water has a 10 centimeter orifice right here at the bottom where water discharges to the atmosphere. Okay, the water level is 2.5 meter above the outlet. So this height is 2.5 meter, and the tank air pressure above the water level is 250 kilopascal, while the atmospheric pressure is 100 kilopascal. So here we are going to have 100 kilopascal right here. So it's open to the air, right? And then they are saying next, neglecting the frictional effects, determine the initial discharge rate of water from the tank. So discharge rate. So we can also say volume rate. Volume discharge rate. Right. So this is like meter cube per second. This one can be calculated by taking the velocity at this point, velocity of the fluid at this point. So let's consider this is V2. So V2 times the area of this circle right here. That is velocity times phi d over 4 square, right? Phi d square over 4. Because this is the diameter. So phi over 2 square. So let's phi over d by 2 square. 2 square become 4 d square. That's how we got this. And this is the value that's going to give us the volume discharge rate. But we know all these things right here, but we don't know the velocity at this point. So we have to find that one out. Since this cylinder is large volume, we can say this V1 right here is 0. So this is the point we are picking right now. So let's pick this point. This V1 is 0 right here. So we can eliminate that one. And here another thing, this is from the reference level, right? This height. So we can say C2 is also equal to 0. Right? So what I can do, I can pick up the Bernoulli's head equation. That is P1 over rho g plus P1 square over 2g plus Z1, right? And this is going to be from here, that's going to be equal to P2 over rho g and V2 square over 2g plus C2. So let's cancel all we can cancel. We know that C2 is 0, we can cancel that one right here. we know that v1 is equal to 0. We can cancel that one right here, and let's continue other things. Maybe I erase this one for now because we don't need this for now. Okay. But I note this one in the side, the equation. Okay, this is v2 times phi d square over 4. That is what we are going to use at last after we finding the v2. So we have p1. So let's rearrange. Our purpose is to find the v2. So let's rearrange this equation. v2 is going to be equal to square root of p, this 2 right here. So 2 p1 minus p2 over rho. Because if you look at it, we have g and everything. We can cancel that one too. So p1 minus p2 over rho plus 2gz. 2gz, right? 2gz. So this is the equation we get. So let's see how we got this one. p1 over rho. So v square over 2 right here. c2 is cancelled already. And if I bring this to the other side, what's going to happen? p1 minus p2. Right? We have p1 minus p2 over rho. And we have a z right here times 2. And also, so when we cancel this one, g and everything, like we are going to have a g right here. That's how this one comes. So we have 2 times p. So that's great. If I put a g, I can cancel everything. Because the thing we did was we multiply everything by g. That's what we have to think. So that's how we can cancel this all g. So this one have a g. That's how I got a 2gz1 right here. So this is the derivation of the equation. Now we have all the values. So let's put it all right here. 2 times p1. Here the pressure is 250, right? 250, and this is open to atmosphere. So they have given this 100 kilopascal. So we can put that one right here. 100. Since it is kilopascal, we can multiply by 1000 pascal. I'm converting kilopascal into pascal. That's why I multiply by 1000. And then we have density of the water in the bottom. We know the density of water is 1000 kilogram per meter cube. So I can multiply that one in the bottom, 1000 kilogram per meter cube. And we have 2 times 9.81 acceleration due to gravity. 2 times 9.81 meter per second square. And z1, the height of this one, that is 2.5 meter times 2.5 meter. And let's calculate all this value. If you plug this all this in calculator, this one is easy, right? This one 1000 cancels. We have 150 left, times 2, 300. And if you convert all the units, you will get meter square per second square. How do you get it? We know that Pascal is equal to Newton per meter square. Newton can be written as kilogram meter per second square, and we have a meter square right here. And this will become kilogram meter minus 1, second minus 2, right? And we have a kilogram meter cube. So kilogram cancels, and this meter cube go to the top and become meter cube, because this is divided by meter cube. So in the bottom it's going to be plus meter cube. So this will become meter square second minus 2. That's how we get meter per second square right here. Meter square per second square. Plus this is direct. We know that meter time meter square second square. So plus, if we multiply all these things together, that's going to be 49.05 meter square per second square. And if we add them, this is going to be 349.05 meter square per second square. And if I put a square root both of them, that's going to give us 18.6 83 meter per second. So we have the velocity right now. All we have to do is simply use this equation and find the volume flow rate. That's what we have to find. That's the question, right? So let's do this. So V2 18.683 meter per second times 5 times, this is in centimeter, I have to convert into meter. That's going to be 0.1 meters square divided by 4. And if I calculate this value, this one comes out to be 0.147 meter cube per second. So this is the volume flow rate, and that's what they are asking. Determine the initial discharge rate of water. Discharge rate, volume flow rate, same thing. And that's how we do. I hope you guys liked this video. See you next time.